What if AI could fine-tune itself with minimal data while improving reasoning? That's exactly what Visual-RFT brings to the table. Built on DeepSeek R1's reinforcement learning techniques, Visual-RFT extends fine-tuning to visual tasks, moving beyond language models. Instead of just memorizing answers, it learns by trial and feedback, optimizing through verifiable rewards like IOU for object detection. The result? A smarter, more adaptable vision model that thrives on limited data. Now let's break it down.
Visual reinforcement fine-tuning, or Visual-RFT, expands on reinforcement fine-tuning, which is often used in large language models. The core idea is to move beyond just using labeled data. Instead, we give models feedback to guide their learning. This feedback-driven approach is especially powerful when you have limited training data and still need high performance. Why is this a big deal? RFT has seen success in language models, but its use for vision tasks has been pretty limited. Visual-RFT changes that. It applies RFT to tasks like object detection, classification, and reasoning grounding. Concretely, large vision language models produce multiple responses for an input image, describing their reasoning steps and final answers. A verifiable reward function then checks how well these responses align with correct answers, guiding the model to refine its reasoning. It's a step beyond memorizing right answers. Instead, the model is rewarded for arriving at better answers through a structured thought process. Check out the figures here. Notice the radar plots and bar charts comparing Visual-RFT with supervised fine-tuning, or SFT. You'll see that Visual-RFT consistently outperforms SFT on benchmarks like object detection, reasoning grounding, and classification. In fact, the results are quite impressive. For example, in one-shot fine-grained classification tasks, Visual-RFT improves accuracy by over 24%. And in few-shot object detection, it achieves substantial gains on COCO and LVIS. What does this mean? Instead of simply training models to repeat correct labels, Visual-RFT helps them reason, adapt, and learn with less data. That's a major shift in how we fine-tune vision models. Now let's think about why this approach matters in practice. Most AI models rely on large labeled datasets for fine-tuning. But what if you have limited data? Visual-RFT steps in with reinforcement-style training. Rather than memorizing annotated examples, it learns from feedback and uses minimal data, sometimes just a few hundred samples. Look at figure XXX here, where various fine-tuning methods are compared. You'll see how methods like visual instruction tuning heavily depend on big datasets to adjust performance. Visual-RFT, however, generates multiple answers, uses reasoning to evaluate them, and then fine-tunes based on a reward function that values the quality of both the reasoning and the final answer. It's the difference between rote memorization and active problem solving. For instance, in object detection, the model might have to identify a Pokémon performing an action. It gets feedback not just on whether it labeled the Pokémon correctly, but also on whether its bounding box and reasoning steps were logical. The same logic applies to classification tasks. The model won't just say, "It's a rose," it'll explain how it recognized certain petals or colors. That's the key insight. By emphasizing why, Visual-RFT trains models to adapt quickly with fewer labels. So how does the model actually think through its reasoning? Visual-RFT sets it up by giving a question and an image. Maybe the question is, which part of this vehicle can be opened? The model won't just guess the doors. It actually explains why doors are typically placed on the side and near the top. Then it identifies that region in the image. Or consider classification. The model might be asked to recognize a type of flower. Instead of just blurting out columbine, it describes the colors, the petals, and the presence of an insect that often visits that flower. The magic is in the reward system. A verifiable reward checks whether the bounding box is right, whether the classification label is correct, and whether the reasoning is coherent. This iterative feedback loop helps the model refine its answers over time. It's a departure from standard fine-tuning approaches that learn primarily by matching labeled examples. With Visual-RFT, each trial and error step strengthens the model's reasoning capacity. You might wonder, how do we get the model to produce these well-structured, step-by-step answers? That's where carefully designed prompts come in. For object detection, the prompt explicitly instructs the model to give a bounding box with confidence scores and to explain its rationale. If it finds no relevant objects, it states that clearly. For classification, the prompt guides it to describe features it notices, like shape, color, or habitat, before deciding on a final label. Now take a look at the explanation of reinforcement learning with verifiable rewards on this page. This is where the model generates multiple candidate responses, and the reward function scores their correctness. It then uses group policy optimization, or GRPO, a strategy where several responses are compared, ranked, and reinforced based on how close they are to the true answer. This keeps training stable and helps the model converge on high-quality reasoning. So the key message? By combining structured prompts with a reward mechanism, Visual-RFT trains models more efficiently than simply throwing millions of labeled samples at them. It's about honing logical steps, not just memorizing labels. Now let's talk about explaining why a classification is correct. Traditional SFT might just say, that's a globe flower, and if it's wrong, it doesn't really know why. Visual-RFT, on the other hand, explicitly walks through the identifying features. Check out the examples here. In one case, the SFT model mistakes a buttercup for a globe flower. Visual-RFT correctly labels it by describing the actual shape and color in detail. Why does Visual-RFT perform better? It has multiple components in its reward system. One part is an intersection over union metric for object detection, ensuring the predicted bounding box lines up well with ground truths. Another is the confidence score, rewarding the model for being correct and certain. It also enforces a specific format for answers, nudging the model to provide structured, logical responses. In this way, Visual-RFT doesn't just boost accuracy, it encourages the model to form a mini explanation. That's the secret sauce that helps it avoid the silly mistakes we often see with models relying purely on memorized patterns. If you flip through another set of examples, you'll see something interesting. The model goes beyond simply labeling what's in an image. It explains the context. Imagine seeing an athlete in a pool. A basic SFT approach might not mention goggles or why they're necessary. Visual-RFT, however, connects the dots, recognizing the athlete is underwater, noticing her expression, and concluding that goggles are important for clear vision. It's that extra layer of reasoning that sets Visual-RFT apart. How does it achieve this? The feedback loop rewards answers that come with strong, logical explanations. If the model's reasoning is off, the reward function reflects that. Over time, the model figures out that thorough explanations lead to higher rewards. So if you see the examples with a bird perched on a branch, or a football in a player's hands, note how the Visual-RFT output is consistently richer in detail. It's not just labeling objects, it's narrating why those labels make sense. One of the best tests for any model is when you only have a handful of training examples. How quickly can it learn and generalize? Flip to the data here on fine-grained classification. The model tries to distinguish between flowers that look almost identical or aircraft that only differ slightly. If you rely on just one or two training examples, SFT tends to struggle. Visual-RFT, by contrast, adapts quickly. You might see a 37% improvement in one-shot learning scenarios. That's huge. The same pattern appears in object detection tasks on Coco. Visual-RFT jumps ahead by over 14% in one-shot settings. As you increase training samples, Visual-RFT keeps a sizable lead, showcasing that it doesn't just memorize, but genuinely learns how to interpret new information. So if you ever need to train a model in data-scarce conditions, Visual-RFT's reinforcement-based approach gives it an edge. Now let's dial the difficulty up a notch by introducing rare categories and out-of-domain data. Always a challenge. Look at the LVIS dataset full of uncommon objects. SFT often fails to recognize them with so few examples. Visual-RFT, meanwhile, scores up to 56% higher than SFT. The MG dataset goes even further by mixing in mythical creatures or unusual animals. Again, Visual-RFT shines, showing how it can handle truly unfamiliar concepts. Another tough one is the LISA dataset for reasoning grounding. Models need to connect visual cues to logical conclusions. Visual-RFT isn't just slightly better here. It exceeds previous models by over 10%. And if you're curious about open vocabulary detection on Coco, where the model identifies categories it's never trained on, Visual-RFT again demonstrates significant gains. The takeaway? Training with feedback and reasoning proves far more robust than standard fine-tuning approaches. Ever see a model completely fail on categories it's never encountered? That's the Open Vocabulary Detection Challenge. LVIS has rare objects like a futon or a sugar bowl. An SFT model might score 0, because it has no clue what those items look like. Visual-RFT, on the other hand, can push that score way up, sometimes over 60% higher, simply because it has learned how to reason about shape, context, and potential use cases, rather than memorizing a single label. Business. This ability also translates to broad, open vocabulary detection tasks. The model confidently identifies objects not explicitly labeled in training. The reason is straightforward. When a model learns to reason visually, it's not limited to the categories it's seen before. That's why Visual-RFT is considered a game changer. It's about fostering genuine understanding in a model, not just pattern matching. Finally, let's wrap this up. Traditional fine-tuning relies on big labeled datasets and manual annotations. Visual-RFT shows there's another way. It uses reinforcement learning principles with verifiable rewards to guide how a model reasons about images. This leads to major gains in classification, object detection, and reasoning grounding, especially when data is scarce. Comparisons show that Visual-RFT generalizes better. It recognizes rare objects, adapts to new categories, and handles complex reasoning tasks that can stump older models. Because it rewards good reasoning rather than just correct labels, it achieves a depth of understanding that pure supervised approaches miss. So, the big message? Visual-RFT takes the core ideas of reinforcement fine-tuning and brings them into vision language modeling. It teaches models to learn smarter, not harder, and paves the way for AI that really understands what it's seeing. Thanks for joining us today. Happy exploring!